romanzi interi uscirra vehementi, in amardudine loquor vehementi, factus de metere azinis elementi, similis foleo dec volundum venti, cum si tenim proprium viro sapienti, supra petro ponere sede fundamenti, stultus ego comparo fluvio lamenti, subeo de tramite nunca permanenti.
Okay, so we're going to continue with the array-based list that we were designing. We designed it, we implemented it a little bit, we tested, we went back and forth on each one of these things. And we left it off with this task right here, that we were going to shift things down. Remember that we're adding an element at an arbitrary index. So that allows you to insert it at the front or in the middle or wherever, right? And we need to potentially shift things down to make room for that element. So I'm going to whiteboard this a little bit before we decide how this gets implemented. Suppose that we had 10, 20, 30, and 40, right? And we want to insert 42, add 42 at, say, index 1, 0, 1, 2, and 3. Now, first of all, we're going to have to make sure that it's expanded, right? We've already done that, though. And so there's plenty of room to make way for this if we were to shift things over. But ultimately what we want it to do is make sure that it's right there. That means I'm going to have to, could I start at this location? Could I say 20 gets shifted over here? What happens to 30? It's gone, right? So what I need to do is I need to start at the end, at the rightmost part, and I need to copy things over one by one. So what we're going to do is we're going to copy 40 over. Now that we've copied that over, that leaves enough space here for 30. Right? Yep, let's go ahead and get rid of all that. Now we can copy over 30. Right? Now that means that 30 can be overridden. So we'll go ahead and copy over 20 there. Right? At that point, now we have enough room to put 42 down, and it's successful. Okay? So what I want to do is I want to start at the end and copy things over by one until I get, and work my way from the right to the left until I get down to that index. So that's going to be a traditional for loop, but it's not going to be starting at 0 and then moving its way up. Where is it going to start? At the end, and so where should I start it? This dot size, okay, right. And where do I go down to? I'll come back to that. Remember I minus minus because we're working right to left. And I'm going to copy over into this dot ARR sub I plus 1 is equal to this dot ARR sub I. I'm just taking the ith one and moving it over to I plus 1. Right? Now, where do I go down to? So where did I go down to in this one? I started down here at index 3, 2, 1. I was inserting it at that index. So that needs to match it on the last iteration. While I is greater than or equal to index, I will shift things over. All right. Let's come back over here to the demo, and let's see if it works. Let's go ahead and kick this back down to 100 so that it's inserting 10 through 100 by increments of 10. And then we'll go ahead and get rid of this. And what we'll do is we'll insert 42. So list.add element 42 to index 1, just like I did in the example that we just did. Now remember that I don't have a way of testing this, ad hoc other than my debugger right now, which is perfectly fine. Let's switch over to the debugging perspective here. And oops, what happened? It threw an index out of bounds exception. Index 10 out of bounds for length 10. Okay. Let's come back over here. Let's see, where does that actually occur? Let's go ahead and run this again, just straight up. Did I remove something, or did we not add element at line 45? Okay, nope, it's definitely this wrong here, right? So, what's wrong? Where should I have started this? Let's come over here, right? Remember that the original size here was what? Before I inserted 42, it's going to be 4. So if I start at index 4, where am I starting here? Yeah, I need to start where? At -1, right? It's that classic off by 1, right? So -1 there. Let's just go ahead and run it straight up to see if it works. Stop everything. Straight up to see if it at least works. All right, done. Okay. Now we can go ahead and debug it and see, did we successfully add, oh, come on. There we go. All right, just a temporary thing. Did we successfully add 42 to index 1? Well, predict, what should it have been before I highlight this? There's 10 through 100 before, and I inserted 42 at index 1, so it should be 10, 42, 20, so that I'm not losing elements, 30, 40, and then the rest of them up to 100. And the size is correct also, 11. Right? Is that the only thing I should test? Adding it somewhere in the middle? Test corner cases or extremal cases. What happens if you add it at 0? Right? So once again, let's go ahead and fire up our debugger and see, does it insert it at 0, 42, 10, 20, 30? Yep, looks like it to me. All right. What else should we test here? And by the way, this is ad hoc testing. You should be putting this into JUnit tests so that you don't have to rerun it every single time. Right? What if I wanted to add it to the end? 10? That should be okay, right? And is it? 10, 20, 30, 40, 50, 92, 100, and 42 at the end. Looks like it to me. Right? I should probably also test, aberrant test cases where, what if you went to 11, right? That should throw an exception, right? And we already looked at how we should do that in a JUnit, right? That you've got this lambda function. Let's look at the tests here. You've got this lambda function that you can run. Where is it? Assert does not throw or assert throws. Where was it? Assert throws, a runtime exception, and then this lambda function where you're getting an element that shouldn't exist. All right. I am convinced that it is correct so far. But before we move on, what I want to do here is I want to really give it a test here. Right? I don't want to go just 10 iterations. Let's go ahead and go with 10,000 iterations. Okay. Can I add, let's go by, I'm going to change this to 1 up to n, and then we're going to go up by increments of 1. So we're going to end up inserting 10,000 things into this thing. And is it quick? Looks like it's pretty quick to me, right? System.out.println. Again, this is just ad hoc testing, but this is what's called kind of a load testing. I'm giving it a workout, right? What happens when we've got many users? What happens when we've got a lot of data, right? 10,000 is not a lot of data, but Yeah, that looks pretty quick, right? All right, well, what if we went up to 10,100, 1 million? I would expect that to be slower because that's more data. That's 100 times more data, right? But it's not going to be terrible, is it? I should say starting. Right. And then have an ing. And then have a true ellipse, 3 dots there. Why is it so slow? A Java array list isn't that slow. Why is my crappy design slow? Right? So let's come back over here. We're done testing for now. Let's come back over here. And remember what happens when you add an element? Occasionally you need to copy things over. You're doing that every 10th element, right? Means that you're doing this 10,000 times, that you're expanding it. That's actually quite expensive. What if instead we were to do this only every 1,000 times, right? Instead of doing it every 10 times, we're doing it 100 fewer times, right? We're expanding it a little bit more, but we're doing it only 1,000 times instead of 10,000 times or whatever it is. Right? Now it's a little bit more tolerable, right? It was still noticeable, a couple of seconds, maybe 1 second there, but it got done way quicker, right? All right. What if I tried something else? That one little line of code, what did I just do? Instead of adding it to the end, where am I adding it now? At the beginning. All right. So let's test this now. How long do you think I should wait? A few minutes, a few hours, a few days, a few years, a few decades. Try, right? It will be a few decades. If not for 1 million, then for 10 million or 100 million. It will be decades. Why is that so expensive? Well, we're going to be coming back to that, all right? Okay, but for now, just know, whoa, that's terrible. We shouldn't be doing that, right? Okay, let's finish our implementation though, and then worry about efficiency, right? What else do I have to do? I've only got one to do left. Nope, that was Friday. So we're done with that. Right. And then we've got get element, replace element. That should be really, really easy. Right. So what's the first thing I should do though? Yep, bounds checking, exactly. If the index is negative, or if the index is greater than or equal to the size, right? Equal to because you're asking for something that doesn't exist. If there are 5 things in there, you can't ask for the 6th thing, 0 indexing. Throw a new runtime exception. Runtime exception. Cannot replace element at index plus index. Now you might, we've done this a couple of times already, right? Every time we come into one of these index-based, we check the indices. Well, maybe we should put that into a function. That one is going a little bit too far because sometimes we check less than or equal to, sometimes we check or greater than or equal to, sometimes we only check strictly less than. But in every single case, we're giving it a different message, right? No such element at index, cannot replace element at index, cannot insert element at index, right? So if it's a different type of error and a different type of message, then yeah, you're going to have to repeat the code. Right? It's not really a repetition anymore because you're not repeating code. It's a unique message every single time. All right. This dot array of index is equal to x. That's it. Do I have to change the size? Oh, I took something out. I put something back in. Do I have to expand or contract? No, right? Because if you ask for something that doesn't exist, then we throw an exception back at you. Otherwise, it was a valid value. Except that now I really want to rethink my design here. Void, right? It's not going to return anything. What could I return instead and make this a little bit more useful? So there's 10 there before. You replace it with 42. What happens to 10? It just gets thrown away, right? What if we were to return it? I'm going to go big I integer here for a reason that we'll discuss later on, right? Right. Big I integer. returns the value that was replaced. Okay. Return this dot array of index. Can I do that? I just replaced it, right? So what should I have done before I replaced it? Or int result. Int result is equal to that thing, and then you can return the result. Okay. I should go big I integer on this too. For later, we'll understand why later. All right. That's it. Remove element. Okay. Well, let's outline it first. 1. What's the very first thing I should do? Check bounds, right? Check the index bounds, right? Maybe also at this point I want to change my design here as well, because if you remove it, we'll go ahead and give it back to you, right? Remove the element at that index, but I want it returned to me, okay? So at some point I'm probably going to save the element to return it, right? We'll go ahead and do that as number 2 there. And then finally at the very end, x.return the temp value, right? Okay, let's visualize this. Once again, let's go ahead and suppose that we have 10, 20, 30, 40, and say 50. And we want to remove index-based remove of 2. 0, 1, 2, 3, 4. So like I already said, we're going to put this into a temporary variable. Right? And then we're going to get rid of it. Do we want a gap like that though? No. So what should we do now? Shift these things down. Right? So the same basic idea as before, but we're going to work from the current index up to the end of the list. This is going to be a more traditional for loop here. Right? So 3, shift elements down to the left. Dot, dot, dot. Okay? Check bounds. If index is less than 0 or index is greater than or equal to this dot get size, right? And we've got a problem. Right? Return, or not return, but throw new runtime exception cannot remove element at index plus index. Completely different error message, so it's okay to repeat ourselves there. Right? Save the element and return it. We know that it's in bounds, so we can go ahead and save it. So integer result is equal to this dot array of index. Okay, and then eventually return it. Return result. Okay. And of course, remove the cruft. I'm leaving the cruft in there so that for demonstration purposes. Obviously, if once you turn this in, you would get rid of each one of those outline steps there. Okay. How do I shift elements down? It's going to be a more traditional for loop. I starting where? 0. Yeah, at the index that you want to remove. I is less than something. I plus plus. And I'm going to be moving the I plus 1th element into the ith element. So this dot erase of I is equal to this dot erase of I plus 1. The one move from over here, it gets moved over here. Right? So where do I go up to and including? This dot size. Okay. Let's work that over here. Right. Get rid of that. All right. So where did I start here? I was going to be 2. And what I did is I copied over 40. Right? I was 3, and so I copied over 50. Should I have gone to I at 4 and copy over something that doesn't exist over here? Nope. So, no. I want to go up to 3 in this case. Now, how big was the array before? Or how big was the list before? It was 5. So I want to go 2 less. All right? Or 1 less than size minus 1. So if this is going to look like a more traditional for loop, it's going to look like that. I could say up to and including down by 2, but that's a what 2? What? All right. There, that looks way more like a traditional for loop there. Okay. Did it work? Once again, let's come over here and let's go ahead and say list.remove element at index 1, say. So we're removing 20 in this case. And let's see if our debugger tells us. Looks nice. We inserted 10 things. Oh, did we insert 10 things? Yeah, we did. We inserted 11 things, sorry. No, it's 10 things. So why does it say 10? We'll find that out here in a second. 1, 2, 3, 4. 2 is gone now, right? 3, 4 through 10 have been shifted down. Great. Stop. All right. There's something fishy still. It says it was of size 10, but it should have been what? Of size 9. What did we forget to do? Subtract this dot size minus minus. Good. All right. Proactively debugging. All right. If you didn't want to use your debugger to do all that, what else could you have done? You could have printed it out, right? In fact, that seems like functionality what you should have. Should we have it in the public void print this list to standard output? Is that the, do we want to make that function? No. What should we make? ToString, exactly. Exactly what we were looking for with, you want to print out an invoice to the standard output? That sounds like an invoice thing. Where should it be? In the invoice class, in the ToString method. You want to print out a service. That sounds like a service thing. Where does it belong? In the service class. Right? All right, so I'm going to go ahead and do this as a string builder because I want a mutable string. New string builder. String builder. Right? And then ultimately return sb.toString. And then how do I format this thing? Well, I'm just going to go ahead and concatenate them all together with nice commas and spaces in between them. So for int I equals 0, I is less than this dot size. Get size is better. I plus plus. SB dot append. This dot array, so I. And then we'll SB dot append. A nice comma, space after it. And come over here, and instead of running my debugger now, I can say system.out.println list. Run that. Nice. Doesn't look perfect though, right? We've got our trailing Oxford comma here. How could I get rid of that? Yeah, stop one short. All right, and then at the end, print out the last element. All right. This dot, or what is it? This dot size minus 1. There we go. And also maybe sb dot append. Put a nice ending bracket at the end. You don't want a curly bracket though, do you? What would a curly bracket connote or denote? I guess a set, exactly. All right. So we don't want that. We want square brackets. Let's come over here and test it. Oh, great! It works. Is there an extremal case, a corner case where this might fail? Oh, an empty list. So let's try to print it out before we even insert anything into it. What do you think is going to happen? An index out of bounds exception. Why? What is the size? 0. This doesn't actually get executed, but this does. 0 minus 1 is going to be minus 1, right? So, if it's an extreme case, a corner case, then that means that you should probably have corner case code to deal with it. If this list is empty, then I will say return, I don't know, empty, something like that instead. How do I determine if it's empty? Okay, this dot size is equal to 0. I agree, but is there a better English way that I could have had that? What if I gave myself some functionality like that? Public Boolean is empty, right? Return that statement right there. Parentheses aren't necessary there, but they're nice. This dot is empty. Right, now I can use English to describe this, right? If this list is empty, then I will return empty, right? That's so much nicer. Empty, and then there we go. Cool. Right. What else would you want to put into this list if we had more time? Right. In fact, we have more time. You'll get to choose some of these things if you want. Right. Other methods that might be nice. Bulk add or remove methods. That is like, say, add all, right? Or remove all. Like you just want to empty the list entirely, right? What else? If you were shopping for a nice list, what would you want in that list? If you were shopping for a car, what features do you want? What features do you want in your list? Sort maybe? Sort question mark. We'll come back to that. Yeah.
Add another list to it.
All right. So add all, like append a list, right? Right. Or insert or merge entire lists, right? Somehow. All right. You could cut and paste it. So if you've got 10 things here in another list with 20 things, I want it right in the middle, right? Go ahead and put it right there. That'd be cool, right? The opposite of that, of course, would be sublist, right? IJ. So that could return a new list from I inclusive to J exclusive, because that's how things work. It's always inclusive, exclusive, except from PHP, and PHP sucks, right? What else? Maybe a copy constructor that makes deep copies of the list. Right? That'd be nice. Right? Add to start end. We already have one of those. We have add to the end, but we could put in add to start. Right? Functionality to shrink the array if too much space is wasted. All right? Basically, all you need to do is look at the list interface, and wow, that'd be nice to have that thing right there, right? And by the way, the list interface has changed over the years. They've added more and more functionality because they want it to be more and more useful. Which one of these things, other than sort, because we'll take care of that later, which one of these things do we want to see today? Maybe choose one. Sublist? Okay. Let's do a sublist. I don't know where to put it. Let's go ahead and put it down here. You can reorganize them later, right? So this would be a public value or a public method, and it would return an integer array list, right? A new one, right? Sublist, right? Or get sublist or whatever. Int I, int j. Right? And now let's document this so that we know where we're going here, right? Returns a new deep copy of list of this list that consists of elements I, code I, through, and then that we're going to put inclusive there, inclusive through j exclusive. Right, there we go. So for example, and again, let's whiteboard this design, right? What is our expectation here? Say it's 10, 20, 30, 40, 90, 80, 90, 100. And this is going to be 0, 1, 2, 3, ... This will be 9, 8, 7. Right? So let's suppose that we want to go from 2 to 8. Right? Remember that it's inclusive. Have you seen this mathematical notation before? Right? In math, if it's a square bracket, it's inclusive. If it's a parenthesis, it's exclusive. In other words, it does not include that one right there. So in other words, it would include everything from 2 up to 7 right there. That one right there. Right? That's our sublist. Okay? All right. So let's come over here. I need to, of course, create a new integer array list. Result is equal to new integer array list. And all I need to do is go from I up to but not including j and just add them. Right? That's it. For int I, index is equal to I. Maybe it would be better if you called this start end, right? But I've already made my choice. I'm going to live with it. Right? So we'll start at I. Index is less than j, exclusively less than j. Index plus plus. Now I'm really regretting I and j. Whatever. Result dot add element. Right? What? What would be this dot array of index? There we go. And then return result. Okay. Let's come over here and see if it works. I'm not going to remove that element anymore. Instead, what I'm going to do is I'm going to say sublist is equal to list dot get, or what was it, sublist from, we said 2 to 8. And let's go ahead and print that out now. That's list. 3 through 8. I had increments of 10 here, but it's the same thing. It's 30 through 8, but we had 10. So, looks like it works. Looks like it works to me. Right? Was that so hard? Is there a better way that we could have done that, though? Right? There's not a built-in one, like a copy of that would start. Maybe let's find out here. Arrays dot copy of the original new length. It does not. Oh, there we go. Yeah, a copy of range. Good job. This dot array, and we'll go up I to j. That's going to be the array, though, right? So int There we go. There we go. That's not going to replace my array, right? Remember, I am the original list right now, right? What I want to do is I want to get that into the result and then return that result so that I don't have to do this thing right here. Right? All right. Fine. How could we do that? I've made a copy of the underlying array. I also know the size of that, right? So what could I do? A constructor. Let's go back up here and say, okay, well, that's my default constructor. What if I had another constructor that took an integer array, right? And I don't have to create a new one. I could just say it's equal to that one. And my size here, of course, would be arr.length or something, right? Should it be public, though? I don't want anybody to just add an array like this. Maybe I do, I don't know. But array, or make it private. Right? And now what I can do is I can come down here and pass off BRR to this thing. BRR. There. Does it still work? Yep, still works. But far fewer lines of code. I'm using something built in, which is always better, right? Because that stuff is optimized. Like I said before, it probably is making a mem copy. Oh, otherwise it's calling clone. What does clone do? Okay, that's just an, oh, yep, it is native. And it's an intrinsic candidate. Anybody know what intrinsics are? Yep, it's specified to the chip. That there's this thing is a candidate. Compiler, check to see if this particular chip that you're running on supports a fast version of this, right? And then it's that. I mean, that's the development over the last 15 or 20 years. It's called vectorization, right? Vectorization, where you do the same operation but on like 1,000 floating point numbers. It's got a pipeline that it can do it all 1,000 in one go, right? Because it's an entire vector of things. I don't know if there are any vectors that big, but whatever, right? And then what else did it have? Copy of int range. And that ends up being a system.array copy, which is another native and intrinsic candidate. It's going to be way faster than what we had. Right? Okay, that's nice. Do we want one more? How about remove all? That should be easy. Public void, remove all. What do you need to do? Oh, it's called what? Remember that we only have access to these, right? You could remove element. So I could iterate over each element and call remove element. Remove the 0th element. Remove. Right? So for int I equals 0, I is less than this dot size, I plus plus. I'll say this dot remove the element at remove element at the 0th index. Right? That'll get the job done. Right? But is there an even better way? Well, not even a new list. Just go ahead and leave the old one there. Right? You're done. Right? You don't have to do any. I mean, don't do unnecessary operations if you don't have to do them. Right? Those values will be overwritten at some point. Right? If you start adding stuff. Right? But now it's just size. Right? Let's see if it worked. So there's our sublist. Let's go ahead and go with the original list. Remove all, and then let's go ahead and print out that list. It should print out empty. Of course it will because it was 0. Right? Empty. Done. Right? Don't write more code than you have to. Right? All right. So here's another improvement. My question is, what is my integer array list, or I guess we called it integer array list? What is it good for? Only integers. Right? And then a happy. I didn't write that. All right. So apparently, Markdown will render a sad face smiley there. Does it do a happy face smiley? Okay. Does it do a weird face smiley? Like, I don't know, 8? Like that? No. All right. It's limited. It only does that. Right? Oh, that this is sad. Right? How do you get angry? Oh, there we go. Yeah. There. That's even better. Hit that angry sad face. Right? All right. So emojis are stupid. All right. All right. So it's only good for integers. If I wanted to do a version of this for strings, what would I have to do? Anytime you see integer here, replace it with string. What if you wanted it for doubles or integer or invoices? Every time you see that, copy, paste, change? No, we do not copy, paste. Instead, we parameterize. All right? Let me rename this, though. I should call it my array list. And let's go ahead and rename the file. There we go. There. In fact, no, let me back that up. Undo. Right. Let me go ahead and create a copy of this because I really want to show you the only differences here. We're going to call this my array list. Right. And T. Okay, I can't do that. I'll have to do it over here. All right, we're not going to parameterize that one. Instead, we're going to parameterize this one. Right. My array list. Okay. It no longer holds integers. What does it hold? T's. Right? Size, that doesn't change. If there's 5 invoices in there, it's still 5 invoices. Right? We're going to come back to this one because that's a little bit tricky. We can't do this though. Like T's. Right? There we go. That works. What else needs to be changed? Add element. It's not an integer. What is it? It's an element of type T. T. Maybe I will go back and change it now. All right. So can I do this? Java doesn't let me do it. The reason Java doesn't let me do it is it needs to know how many bytes it takes. Right? Now, if this were an integer, it knows that it takes 4 bytes. So it knows that 10 times 4, 40 bytes need to be allocated. If this were a double, it knows that it takes 8 bytes, and so 80 bytes needs to be allocated. If it's a T, as stupid as Java is, it doesn't know how many bytes that takes. It should. If it were object, it does know how many bytes that takes. Right? And every object is 8 bytes because it's a reference, a pointer basically. Right? But Java doesn't know that. Right? So what we have to do is we have to force it to become elements of type T. Right? Come on. Change cast to... Oh, no. Duh. There, that's why. What did I do before? That's a two-dimensional array. Right? This is a single-dimensional array. There we go. Right? That's a little bit better. I don't want that either. There we go. I just made a mistake. Sorry. All right, so objects, Java can do that, right? You can create a generic array of objects and you can put whatever the hell you want in there. And it knows that because it's 8 bytes, right? But I want it to be forced to become elements of type T. If I didn't have that, I think it would be a compiler error because an object is not an element of type T. There are historical reasons for that. We didn't have parameterizations in the first 4 versions of Java. And so the way that they did it is that this is a compiler check, right? There's some history there. But anyway, what else needs to change now? Did any of that code need to be changed, by the way? No, just that guy right there. Does any of this code need to be changed? Well, the return type does. I'm not returning elements of integers anymore. I'm returning elements of type T. Return elements of type T. Take elements of type T. That's it. I'm just removing all of the type values here. Oops. Okay, T. There we go. And that should be a T right there. And we're good. Good. No changes, no changes, no changes. My subarray of type T. Parameterize that as well. Right? And this is an element of type T. There we go. And parameterize this as well. And parameterize this. Actually, you don't need to do that. You could just go ahead and go like that, and the warning will go away. No changes at all. Right? Now, there is a warning here that you can pretty much ignore that. Add suppressed warnings is how I would usually do it. There's an unchecked type exception there, or type warning there. Right? But now, look at the difference between these two files here. You can do that by highlighting multiple files and going down to compare with each other. And it'll do a git diff basically on it. Right? What did I change? The only thing I changed, other than a little bit of white space here and there, was anytime I referred to an integer, I changed it to a T. Right? Cool. No code changes at all. Over here in the demo class, now I should of course change this to my array list of elements of type integer. Right? And then change this to my integer array list. Reified, is that what it's called? Yeah, it's, you can abbreviate this and not have to put this in. It's called reification. I think it's called reification. Maybe I'm wrong on that. But it's reified that you don't have to repeat yourself, basically. Right? Then what else? Of integers. There we go. And that's it. There. Everything works as before, but now what did I gain by doing that? I can reuse the same class for strings, right? Names is equal to new, whatever. And names.add me. Names.add, or elements, sorry. You. Element. Right. Not only that, but what am I not allowed to do now? 10. Right? That won't work. Right? 10 will work. TEN will work, but that's a string. Right? I have solved this list problem forever, right? At least for array lists. Right? Now, of course, in real life, would you ever write your own list like this? No, unless it's an assignment, and that is your 7th assignment. So you would write your own list for this class. But in real life, you would never actually do this. You would use the built-in array list or list. Right? All right, so That was pretty easy. What is my array list good for now? Everything. Right? Yay. And now it is a happy face. Can I get like a... No. No. Something like that? I don't know. Fine. There we go. Happy. Okay. There's still a problem though. All right. Let me come back over here and do that same load test again. All right. So 1 million elements. 1, 2, 3. Right. And if we always add it to the end, we're fine. But if we add it to the beginning, we're not. Right. This will take literally maybe years or decades. Why? It's only 1 million elements. Is 1 million big data? No. It wasn't big data 20 years ago, right? It was big data maybe 40 or 50 years ago, right? But it ain't big data today. That is intolerably slow. Why? Let's look over to add element. Index bounds checking, that's nothing. Right? Check the capacity and expand if necessary. Every 1,000 elements, 1,000, 2,000, 3,000, 4,000, 5,000. In other words, 1,000 times, what do you end up doing? You end up making a copy. Right? Well, that's only 1,000 times for 1 million elements. This is the real culprit right here. Right? What are we doing every single time we add something to the beginning? We're shifting everything over, right? So, at the very beginning, that's fast, right? If the size, let's go with that. If the size is 1 or 2 or 3, how many shifts do we do? Shifts. There we go. We do 1 shift, 2 shifts, 3 shifts, ... 1 million. I'll just go 1 million. 1 million. 1 million shifts towards the end. 1 million is still not big data. It's still not a million operations. But if you're doing this that many times, right? What is the sum total of all of these things? Size I running from 1 up to 1 million of I. Because that's what you're doing. 1 plus 2 plus 3 plus 4 plus 5, ... 1 million. Does anybody know? Now you've done this you've done induction in 235, right? Yes? No? Not yet? Okay, fine. Right. Otherwise, this is Gauss's formula. And this is the one that you always start induction with because it's the easiest proof by induction. This is going to be equal to I times I plus 1 all over 2. All right? Actually, sorry, I should have said n. Right? N. Because I is my index variable in here, right? That thing right there. So let's go ahead and clean that up. This will be n, oops. This will be n times n plus 1 all over 2. Well, what did I say that n was? 1 million. So 1 million times 1 million plus 1 all over 2. How big is that? I don't know. Yeah, millions, or that's 500 billion, right? So Wolfram Alpha. 1 million is 10 to the 6th times 10 to the 6th divided by 2. Get rid of my 9. There we go. And that's 500 billion. Million. No, that's million. That's billion. Yeah, they're 50. Did I get it wrong? Plus 1. Oh, my 5 is wrong. Jeez. Can't type today. And then there should be a plus 1 in here, but that's not going to matter that much. All right, there we go. 500 billion something. Right? So 500 billion operations. That's what we're doing here. Right? So is that appropriate? No. Right? Is there a better way of doing that? And that's where we're going to go after the break. Right? So here's an alternative that's called a linked list. What if I stored elements in, you know what, make it look nice, 10. What if I stored them in things called nodes? Right? And each node had a reference to the next node. 20 is in there. And 30 is this thing over here. And it has a reference ... right? Okay? Each one of these things is a node and they are linked together. That's why it's called a linked list. Now, what if I wanted to add something to the beginning? The beginning, that node, we call it the head. Right? All I need to do is create a new node, 42, link it to that one, and update my head to this one. And then pull it tight like a chain. And now 42 is at the beginning. Did that take 1 million shifts? Did I have to shift anything? No. All it is a bunch of memory accesses. So you might ask yourself, why the hell did we just go through that exercise over the last 2 days of creating an array-based list? Right? And it's because this one is efficient for that operation, but it's inefficient for other operations. Right? So this is why you need to distinguish between these two data structures. The difference between a computer scientist and like a boot camp coder is knowing the difference between data structures and when to use them and when not to use them. Right? And so we'll get into that on Monday after the break. All right? Any questions? All right, then have a good break. And